Okay, guys, how are you? I hope that with the continuation of producing videos regarding aerospace dynamics, and we are actually doing it for our channel primarily, which is aerospace engineering concepts, problems, and solutions. And right now, we are dealing with the beginners graduate level courses and simultaneously covering the thesis and also the research papers at postgrad level and at even by various scholars and researchers, and just combining the concepts and providing you the core idea of how the aerodynamics and obviously the applications in the industrial level are normally understood, and how actually it's been approached by various minds or by various sources at various levels. So let's see how we're going to see this video with the concept which is about fluid dynamics, just an introduction and giving some of the details as well. And it's in the semester course of IIT Kanpur. It's the book been taken from the book Barnes, written by actually Barnes W. McCormick, and it's about aerodynamics fundamentals and aerospace fundamentals. So what is it? The author is from the Pennsylvania State University, and let's see what we can have as far as the theoretical portion is concerned when it is being taught in the universities, primarily in IIT Kanpur and in most of the Indian institutes of technologies. The course book is applied all through the institutes, and we're going to cover first of all the theory, and let's see what we can have. Simultaneously we're going to actually catch up with the concepts, and also we're going to work towards understanding and ultimately testing these concepts later in our videos with the help of problems, so that obviously we can see that where we can gauge ourselves, or where we can apply ourselves towards the understanding of the theoretical portion. So let's see, where as the fluid dynamic is concerned, we will now treat a fluid that is moving, so that in addition to gravitational forces, inertial and shearing forces must be considered. And a typical flow around a streamlined shape is pictured, which is in front of you in figure 2.4. Note that this figure is labeled two-dimensional flow. This is a two-dimensional flow, and this means simply that the flow held is a function only of two coordinates, for example x and y in the case of figure 2.4. This is the case of figure 2.4. X and y coordinates 1 2 3 4 5 6 7 8 9 10 and 11. 1 is the negative. At one point it is the negative static pressure acting outward, and number 2 is the positive static pressure acting inward. Number 3 is the stagnation point. There is no such flow. 4 is the velocity vector. 5 is the laminar boundary layer. 6 is the transition point. 7 is the turbulent boundary layer. 8 is streamline. 9 is separation point. 10 is separated flow, you can easily see, and 11 is wake. This is the wake portion. And 2D flow around a streamlined shape. This is a 2D flow around a streamlined shape. So let's see how we're going to see that. First of all, and normally what it has been said that the two coordinates x and y in the case of figure, and does not depend on third coordinate. For example, the flow of wind around a tall cylindrical smokestack is essentially two-dimensional except near the top. Here the wind goes over as well as around the slack, and the flow is 3D. As another example, flow figure 2.4 might represent the flow around a long streamlined strut, such as the one that supports the wing of a high-wing airplane. The 3D counterpart of this shape might be the blimp. In 2D flow, if y of x defines the position of a streamline, y of x is related to x and y components of the velocity, and u of x and v of x by dy over dx is v by x into u by x. Note that the body surface itself is a streamline. Body surface itself is a streamline. In 3D flow, a surface swept by streamlines is known as a stream surface. If such a surface is closed, it is known as the stream tube. The mass flow accelerates around the body as a result of a continuous distribution of pressure exerted on a fluid by the body. An equal and opposite reaction must occur on the body. This static pressure distribution acting everywhere normal to the static pressure P naught in the fluid for far removed from, this is actually number 2, far removed from the body. Near the nose, P is greater than P naught, understandable. Further, all the pressure becomes negative relative to P naught. If this static distribution acting normal to the surface is known, forces on the body can be determined by integrating this pressure over its surface. In addition to the local static pressure, shearing stresses resulting from the body surface, body forces. As fluid passes over a solid surface, the fluid particles immediately in contact with the surface and brought to rest. Moving away from the surface, successive layers of fluid are slowed by the shearing stresses produced by the inner layers. The term layers is used only as a convenience in describing the fluid behavior. The result is a thin layer of slower moving fluid known as the boundary layer adjacent to the surface. We have discussed boundary layer in detail in one of the videos. You can go over there. I'm just reading out the text so that obviously you can understand the point. Near the front of the body, this layer is very thin and the flow within it is smooth without any random or turbulent fluctuations. Here, the fluid particles might be described as moving along in the layer on parallel planes or laminae. Hence, the flow is referred to as laminar. One might reasonably assume that the forces on a body moving through a fluid depend in some way on the mass density of the body, rho, the size of the body, L, and the body's velocity, V. If we assume that any one force, F, is proportional to the product of these parameters, each raised to an unknown power, then force is directly proportional to rho of A, V of B into L of C. In order for the basic units of mass, length, and time to be consistent, it follows that this is how we're going to represent the units. Considering M, L, and T in order leads to 3 equations for the unknown exponents A, B, and C, from which it is found that A is equal to 1, B is equal to 2, and C is equal to 2 as well. Hence, F is directly proportional to rho V squared into L squared. That is equation 1. For a particular force, the constant of proportionality in equation 1 is referred to as a coefficient and is modified by the name of the force. For example, the lift coefficient. Thus, the lift and drag forces L and P can be expressed as this one. L is half rho V squared S of C L, and D is half rho V squared S of C D. This is how you're going to determine. Note that the square of the characteristics length L square has been replaced by a reference area S. Also, a factor of half has been introduced. This can be done since the lift and drag coefficient SCL and CD are arbitrary at this point. The quantity rho V squared by 2 is referred to as the dynamic pressure, the significance of which will be made clear shortly. So, for many applications, coefficient of lift and drag remain constant for a given geometrical shape over a wide range of operating conditions or body sizes. 2 important dimensionless parameters are RE, which is the Reynolds numbers, and the Mach numbers. Reynolds numbers can be shown by this: VLP by mu, and M is V by A, where L is the characteristics length, V is the free stream velocity, mu is the coefficient of viscosity, and A is the velocity of sound. The velocity of sound is the speed at which a small pressure disturbance is propagated through the fluid. At this point, it requires no further explanation. So this is how you're going to, this mu will produces this, which is the shearing stress on wall, represented as force per area, and also written by this, which is the derivative of U by Y, where Y is equal to 0. This is the equation 1. Actually, equation 2. This is what 1 is applicable to calculating the shear stresses between fluid elements and is restricted simply to wall. Yes, this is A, which we have actually referred. This is simply restricted to the wall. Generally, the viscous shearing parallel to viscous shearing stress in the fluid in any plane parallel to the flow and away from the wall is given by the product of mu and the velocity gradient normal to the direction of flow. The kinematic viscosity V is defined as the ratio of mu to rho, and which is this, how you're going to represent it. V is defined as the matter of convenience since it is the ratio of mu to rho that governs the Rayleigh number. The kinematic viscosity for the standard atmosphere is included in figure as an inverse fraction of the standard sea level value. A physical significance can be given to the Rayleigh's number by multiplying numerator and denominator by V and dividing by L. R is rho V square into mu V by L. In the following material, the normal pressure will be shown to be proportional to P rho V square, whereas from equation A, mu V by L is proportional to the shearing stress. Hence, for a given flow, the Rayleigh number is proportional to the ratio of normal pressures, inertia forces to viscous shearing stresses. Rayleigh numbers is high, the viscosity will be low for any flow. So, just going to the Mach numbers determines to what extent fluid compressibility can be neglected. For example, variation of mass density with pressure. Current jet transports, for example, can cruise at Mach numbers up to approx 1.8 before significant compressibility effects are encountered. Mach numbers are low, so two flows are similar if a higher Rayleigh number is same for both flows. For example, CD for a coefficient for a body 10 meter long at 100 meter per second will be the same as C coefficient of drag for a 100 meter long body and 10 meter per second. As another example, suppose transition occurs 2 meter back from the leading edge of a flat plate aligned with the flow having a velocity of 50 meter per second, then at 25 meter per second transition would occur at a distance of 4 meter from the leading edge. Obviously, the effects of R and M on dimensionless aerodynamic coefficients must be considered when interpreting the test results obtained with the use of small models. For many cases of interest to aerodynamics, the pressure field around a shape can be calculated assuming the air to be inviscid and incompressible. Small corrections can then be made to the resulting solutions to account for these real fluid effects. Corrections for viscosity or compressibility will be considered as needed in topics like conservation of mass, which we're going to deal in our next video. The whole topic, which is about the primarily, which is of the fluid dynamics, we have discussed the fluid dynamics in our one of the earlier videos, but the point here is just to deal with the theoretical portion, obviously in a 2D scenario, in a 3D scenario, by giving out the graphical and the expression or the mathematical expression, or you can say it is the mathematical expression or the algebraical expression in front of you, taking the derivative and defining it in different x and y components, and with the help of the Mach number, with the help of all the stuff, we will be able to actually define these two Rayleigh numbers and Mach numbers. Will be able to actually define the extent of the compressibility. So I hope that is well enough to be explained. This is well enough to be explained and worked over. So let's see how can we actually go towards understanding the whole part. So I believe it's been over, and we're going to actually reach out with the conservation of mass in our next video, and we're going to discuss some of the concepts in detail. If you have any question whatsoever, I have read out because I have actually explained some of the cases, some of the scenarios earlier in my video, so that is why that's not a problem for me to actually just go through in a bit. But if you have any questions, you can just check over again with the comment section. I'll hopefully actually reply. And nevertheless, if there is any questions you find out problematic, you can also refer, and we will going to deal out with those problems, obviously, with a video presented. But right now we are moving towards our own actually set targets that we have to actually complete the courses, provided the video, so that in detail we can help you in the long term for the completion of courses primarily. So that is why we are actually providing you the videos on a constant level. So with the help of these videos, you will be able to grab as much as possible whenever you're traveling, whenever you are actually moving from one place to another, and even at your workplace or even at your home. If you are as a student working as a student, if you are working as a student in the university or in the academia, working in the university or outside elsewhere, even we welcome the faculty members anywhere actually teaching such courses to contribute their efforts as well, so that obviously it may help us for the betterment of the channel, which we are actually working towards at the end of the day. So that is how we're going to conclude this video, and I hope that with the with more videos coming up, I'll be actually grateful to the contributions made by the students or made by the faculty member from IIT Kanpur especially, and from the rest of the IITs who are actually helping and providing the stuff and making us available, so that obviously we can extract the ideas which are our own requirement for the business point of view, and also we can provide a healthy output to the channel and also the healthy output to the public as well. So with this note, I'll just end up my video for the next video, which will be on the conservation of mass. Till then, take care and have a nice day.